Okay, so today we're gonna do a review for the the exam next week, which is on Tuesday. Before I start, are there any questions? I guess actually I am anticipating some questions. So, for this exam, you can have a handwritten like cheat sheet, just no worked examples on it, please. So like workflows and things like that that you want to put on there, that's fine. You can also have a calculator. You should have a calculator, a non-programmable type calculator. There's details in the syllabus about calculators that are allowed. And I think that's all. Are there any questions about the exam before we do the practice? Yeah.
Is that sheet that we can use, is that one side or both sides?
Did I say before? I can't remember. Both sides is fine, I guess. You can have both sides. Yeah, okay. Other questions? No? Okay, cool. So,
Yeah.
huh? Oh, yeah, sorry. It'll be the same format as this, yeah. Okay, so let's dive into it. Before we do that, I was just curious, has anybody gone through the exam yet themselves? Oh, good. Very good. I'm so proud of you guys. Okay, fantastic. Okay, so this is a 3-question exam. The points are broken up like this. I know some of you probably panicked when you saw that question 3 was half the points for the exam, but it's broken into like 3 mini questions, sort of all on the same sort of setup. I made some adjustments to this because I realized that I forgot to put this equation. So I've added this one to the actual exam because I forgot it. But this is the equation sheet that I give you with the exam. So I write the exam and I have the equation sheet on the exam such that if you didn't write your own cheat sheet, you'd be fine. Like you don't need a cheat sheet to take the exam, if that makes sense. But you're obviously welcome to have it if it makes you feel better. And then I didn't put it in this, but you will also get a packet with the property tables for the exam. I don't expect you to memorize that sort of thing. Okay, so question 1 is the following. So we have a vertical piston cylinder that contains a gas at an unknown pressure. The piston has a mass of 10 kilograms and an area of 0.1 meters squared. When a 100 kilogram weight is placed on top of the piston, it remains in equilibrium. So if we consider atmospheric pressure to be 100 kPa, determine the equilibrium pressure inside the piston. Okay, so in the first topic, I think we talked about pressure in great detail, so you can expect a pressure related question on the exam. So does anybody have any ideas about how we might start this one? I'm gonna mark this up with some information. So we have this mass, I'm gonna call it M2, is 100 kilograms. This mass, I'm gonna call M1, is 10 kilograms. This area is 0.1 meters squared. And then I'm going to call this pressure inside here. Any ideas on what we should do first? Yeah. Yes, I love it. Thank you, Mark. So let's make a free body diagram first. And I'm going to make the free body diagram of the piston. All right, so what forces do we have on our free body diagram? Yeah, so we have 2 weights. We have a mass of the piston itself. So I have M1G. And then I also have the weight of the mass on top of the piston. So M2G. What else? Yeah, I have atmospheric pressure on the top. So this is P atmosphere. And it has a resultant force that looks like P atmosphere times A. Right? And then similarly, I have the pressure inside of the cylinder. So obviously the pressure is all along the whole bottom of this, but I don't want to make this too hard to read. So I also have P times A pointing up. Does everybody feel okay with the free body diagram? Okay, cool. So now that we have our free body diagram, I am going to use a sum of the forces in the z direction is equal to mass times acceleration in the z direction. What can we say about the right-hand side of this equation?
Acceleration.
There's no acceleration because we're at equilibrium, right? Excellent. So I can say that all of my forces summed in the z direction is equal to 0. So now I'm just going to sum up the forces from my free body diagram. So I have one positive force, which is P times A, and then three negative forces. So I have minus P atmosphere times A, minus M1G, minus M2G is equal to 0. All right, I have been given A. I've been given P atmosphere, I've been given M1 and M2, and then I of course know G as well. All right, so I just want to solve this for P. All right, and so when I do that, I get 1 over A times P atmosphere times A plus M1G plus M2G. Okay. Okay, now I'm going to plug in the values that I was given. So I have 1 over area is 1 over 0.1 meters squared. I have 101 kPa, which I'm going to convert into units that will work for the rest of this equation. So I have 1 kPa is equal to 1,000 pascals. And 1 Pascal is a Newton per meter squared. And 1 Newton is 1 kilogram per meter per second squared. Okay, so what I have here is the following. And then meter squared. Okay, and then mass 1 is 10 kilograms times 9.81 meters per second squared. Bless you. And then I also have 100 kilograms times gravity. So let me just move this over. 9.81 meters per second squared. All right, so my second two terms, I have kilograms times meters per second squared, right? And so this factor of 1,000 here is important because before I had kilogram, 1,000 times kilograms per meter squared, right? So you want to make sure that you're careful when you're combining weights from mass times G when you're using kilograms and then meters per second squared versus when you're using kPa. Okay, so just be careful with that conversion. I can't remember if I've said this in front of the entire class or not. I know people have asked me this. So for the exam, I will be sticking with SI units. So like this is the, closest to a conversion that you'll have to do for the exam. Obviously, it's important to be able to switch between English and metric units, but we practice that on homework. Okay? Okay, so we get from this 111.8 kPa. I don't like how that looks. And that's our final answer. All right, as a sanity check, this is above atmospheric pressure, which is good because you have weights on top of it in addition to the atmospheric pressure. So if it's balancing those things, it should be higher than atmospheric pressure. So that looks good. Any questions on this one? Yeah.
You wrote the atmospheric pressure as 101 kPa. Is it supposed to be 100?
Oh, yeah, sorry, it is 100. Thanks. Any other questions on this one? Is this a fair question? Okay, we approve of that question. Good. All right, next question is a little bit different. So in the first part of this question, we're given 4 different systems and we want to identify whether they're open or closed. Oh, sorry. Yes, Ally.
I was just confused, so it's 100 kPa, but it was multiplied by A.
Oh, yes, sorry. I got all excited about the units and then I didn't put them in here. Thank you. So this is times 0.1 meters squared. There we go. Yeah.
We have to show us, like, they all the unit conversions,
If you want to, so this is good practice to do just to keep it straight in your own head. But if you just write me a note, so if you say like 1 over 0.1 meters squared, and then you have 100 times 10 to the 3 pascals, and then times area, that's fine. Okay. Okay, so for this question, we're given 4 systems and we want to identify them as either open or closed systems. And then the second part of this is solve the problem that's a closed system. Okay. So let's do the first part first. So the first one we have is a piston cylinder system with a gas at a pressure of 10 MPa and a specific internal energy of 5 kilojoules per kilogram. If the system reduces in volume by a half due to a leak in the side of the vessel, but the pressure remains the same, what is the resulting internal energy of the system? What do we think? Open, why? Wait, say again? So it does reduce in volume. It reduces in mass, right, through the leak. So since there is mass flow, it has to be an open system. Does that make sense? Okay. Okay, second one, we have a silicone chip generating 5 kilojoules per kilogram of heat during operation. If a fan is used to cool the chip and the inlet air is 20 degrees C and moves past the chip at a velocity of 2 meters per second, what is the temperature of the air after it leaves the system? Yeah. Open, yeah, why? Yeah, so we have mass flow. So air moves in and out of the system. Great. Okay, choice 3, carbon dioxide in a piston cylinder device is expanded from an initial volume of 0.2 cubic meters to a final volume of 0.5 cubic meters. During the process, the pressure changes with volume according to P equals 3 over volume cubed. Determine the boundary work for this process and indicate whether it is input or output from the system. Closed, yay, great, yes. So we have a closed system. So that's good. Last one, a lawnmower with a 2-stroke gas motor uses 2 liters of fuel to supply 200 kilowatts of shaft work to the blades. If there's no change in internal energy of the fuel, how much heat is lost by the mower to its surroundings? Yeah, so this one's open. This one's a little more subtle, I think. But we have mass flow in this one as well, right? So we have fuel coming in and out from, or in from the fuel lines, and then it's being expended. And then there's also an air intake system from an engine as well. So we have mass flow here as well. Okay. Any questions on the open and closed system categorization? Feels good? All right. So now we want to solve the problem with the closed system. So we're going to solve system number 3. All right. So to remind ourselves, we have a few things given to us. So given is that the initial volume, so volume at state 1 is 0.2 meters cubed, and then volume at state 2 is 0.5 meters cubed. And then we're also given that the pressure during this process changes like 3 over volume cubed, or volume to the -3. And we want to find boundary work. Okay, so boundary work, the equation is given to us on our equation sheet. So we want to use this guy here. And I'll just write it down again. So we're looking for WB is equal to the integral from volume at state 1 to volume at state 2 of pressure dV. All right, so I am going to plug in this expression for pressure that we've been given into here. V1 to V2 is 3 times volume to the -3 dV. What do we get for this integral? I'm going to pull the 3 out because it's a constant. Yeah. Is it positive or negative? Yeah. So we have minus V to the -2 over 2. Okay, and then we're going to evaluate this between V1 and V2. So we have 3 times minus V2 over to the -2 over 2 plus V1 to the -2 over 2. And then I'm going to plug in those values which we have. So we have minus, and I'm going to pull out the half. And then I have 1 . Yeah, okay, I have, oops, minus 1 over V2 squared, so I have 0.5 squared plus 1 over V1 squared, which is 0.2 squared. So we have 31.5 kilojoules. Does this work go in or out? So it's positive, right? So that means that the work comes out. All right. I know that this is hard to remember and it can be confusing because chemistry classes will use an opposite convention sometimes for heat transfer and work. So one way that you can remember this is with the equation sheet, actually. So if you look at this expression for total work, we have work out minus work in. So if the net work is negative, it's generally input. If it's positive, it's generally output. Does that make sense? Okay. Any questions on this one? How did we feel about it? It was okay? Okay, good. Okay, third question, the big one. Okay, so this is our 50-point question that has 3 parts. But the parts walk you through how to solve it. Okay, so we're just gonna go with the flow with what the parts of the question are, and it will be just fine. All right, so we have a piston cylinder with 10 kilograms of water in it. At its initial state, the water is superheated at 500 degrees C and it occupies a volume of 0.05 meters cubed. The water is then cooled through an isochoric process, so no change in volume, to 250 degrees C. And then finally, the piston cylinder achieves a pressure of 4 MPa through an isothermal process, so a constant temperature process. Okay, so I am going to mark this up with a few things. So we have a state 1 statement, which is this. And then we have state 2, which is given to us here. And then finally, we have a state 3. All right, and so I am going to, the first part of this question is we want to essentially determine the properties that are in this table that are missing. All right, and once we fill out this table, we will have all the information that we need to do the other subsequent parts of the problem. Okay, so I'm gonna start with state 1. All right, and let's write down what we have. So overall, we have that the mass is 10 kilograms. 10 kilograms. Okay, so this is a closed system, right? We can all agree. So the mass stays the same. So this is constant since it's a closed system. Okay. And we are also given that its initial volume, so V1, is 0.05 meters cubed. And then we have that the temperature at 1 is 500 degrees C, and its state is a superheated vapor. Right? Okay. What should we do first? Is there anything that we can immediately figure out to fill out our table? Yeah, the specific volume. So we can use these 2 pieces of information to find V1 because specific volume is just the volume divided by mass, right? So we have 10 kilograms, or sorry, no. We have 0.05 meters cubed over 10 kilograms. So this is 0.005 meters cubed per kilogram. Right? So I'm going to put that in here. Okay. And now we know the state, it's a superheated vapor, and we know the temperature and the specific volume. So we should be able to find both pressure and specific energy from the superheated vapor tables. Okay. So I'm going to quickly grab the tables that we need for water and add them into here. So I would like, not that, no. Okay, here. So I want to take this page, this page, this page, this page, this page, this page. Okay. And I'm going to I don't know if that's what I want, but we'll see. Great. Okay. Okay. So now I have all the tables in here. So you would have this on the exam in a separate little packet. So first we're going to go to the superheated vapor table for water, which is here. All right. And we know that the temperature is 500 and we know that the specific volume is 0.005. Okay. So what I'm going to do is, since the superheated vapor tables are organized by pressure cells, we're going to have to kind of hunt through the pressure cells and look for 2 cells that get us close to a specific volume of 0.005 for a temperature of 500. Okay, so if I start off at the very beginning of this table, I'll look and see, oh, for 500 here, I'm at 35, which is pretty far off from what we need, right? So I'm gonna keep going down here. My values are getting smaller, which is good. So we're getting closer. So here for 500, we're at 0.08. We need to keep going more. And so when we get down to the very bottom of this table at 500 degrees C, we have a specific volume of 0.005623 for a pressure of 40 MPa, and then 0.003890 for a pressure of 50 MPa. So I want to interpolate between these, okay? And I'm also going to grab, I want specific volume and internal energy, so I'm going to grab this value as well, because I'm going to have to interpolate that too. Is everybody on the same page? Okay. So I'm going to make my interpolation table with those values over here. So, oops. So I have temperature, specific volume, pressure, and internal energy. All right, so all of these are at a temperature of 500, right? And our specific volume that we want to get is 0.005. The one slightly above that is 0.05623. And then below is 0.003890. And I should have given myself a little more space. All right, and then the pressures. So I want to find P1 here, and then we had 40 MPa for the slightly above specific volume, and then we had 50 MPa for the one that was slightly below. And then we also want to do this for internal energy. So I'm gonna just scooch this a little bit. Okay. So I want to write this down for internal energy as well. And we have 2681.6. U1 is what we're trying to find. And then 2528.1. Okay. Is everybody good with the interpolation table so far? All right. So let's set up our interpolation for P1 and P2, or sorry, P1 and U1. Okay, so for P1, I have P1 minus 40 MPa divided by 0.005 minus 0.005623 is equal to that same slope between the points that we know. So we have 50 minus 40 MPa divided by 0.003890 minus 0.005623. All right, and then I just solve this expression for P1, and I get 43.59 MPa. All right, as a quick sanity check, we look and we say, okay, we're between 40 and 50, which that's good because that's what we're interpolating in between. Generally, if you've made a mistake, you'll not have that be the case. So that's a great check. And we see that it's closer to the 40 MPa entry, which is consistent with what our table shows us. So that's good. Okay, we'll do the same thing for internal energy. So I have U1 minus 2681.6 divided by 0.005 minus 0.005623 is equal to 2528.1 minus 2681.6 divided by 0.003890 minus 0.005623. All right, and then when we solve this expression for U1, we get 26.4. And then this is kilojoules per kilogram. Okay. Any questions on the interpolation or anything so far? No? Okay, so I'm gonna pop these back into the table here. So I have 43.6 MPa. And then U is 26.4. Okay, so state one is sorted. All right, so just to recap the process, I'm gonna follow this exact same process for every state that I'm trying to get properties for. First things first is I want to figure out what state it is. So we already knew it was superheated vapor, so that told us what table to go to. And then we went to that table and interpolated based on the information we already had, which was temperature and specific volume. Okay, so let's do state two now. So state two is the information in orange. So the water is cooled through an isochoric process to 250 degrees C. So we've got 250 C in our table already. What can we also populate based on what that statement says? Yeah, specific volume has to stay the same because the volume stays the same when there's an isochoric process. It means no change in volume. It's a closed system, so M is also the same, so specific volume stays the same as well. So we have 0.005. All right. So that means we have two pieces of information. So we are able to figure out what the state is using those two pieces of information. Okay. So I will put state two here. So we have state two. So we have T2 is 250 degrees C, and specific volume is equal to specific volume at state one, which is equal to 0.005 meters cubed per kilogram. And this is because volume is constant. Okay. So what should we do to figure out what the state is? Any ideas? I heard murmurings, I think. No one wants to be brave? Okay, so if we want to find the state, we're always going to go to the saturated liquid vapor table. And we want to find what VF and VG are. Since we have specific volume, those are the values that we're going to look for to figure out where the boundary of the vapor dome is. Okay. So essentially, we want to find, if this is V, we want to figure out VF and VG, and we want to know where in relation to those two values our specific volume is. Okay. So we are going to use the temperature table for saturated liquid water. Okay. So that is right here. So we're going to our temperature table and we have 250 degrees C, which is this line here. So I'm going to make note of VF and VG here. And I'm also going to make note of my saturation pressure as well. So I'm going to just copy all of this for reference. For here. Okay, so we have that at 250 degrees C, we have VF is 0.001252 meters cubed per kilogram. And then we also have that VG is 0.050085 meters cubed per kilogram. Okay, so where is our state? What can we say about our state, given that? Yeah, it's a saturated mixture, right? So we're in the vapor dome somewhere roughly in the middle. Okay, so this is where our state is a saturated liquid vapor mixture. Okay, So that's awfully convenient because I already have all the information that we need in the table right here. So what we are missing from the table now is we need P2 and then we also need U2. Right? How do we find P2 if we're in the vapor dome? Yeah, so under the vapor dome, our pressure is always going to be the saturation pressure for that temperature. So P2 is Psat at T2. So we're going to look at this value right here. So we've got 3976.2. So this is 3.9 MPa. Okay. All right. And then what about U2? How are we going to find U2? Huh? We could interpolate. We could also use the quality equations. It's essentially the same thing. Which adventure would you guys like to choose? It works out to be the same. Does anyone have a preference? The quality one? Okay. So we will use the quality equations. So what we're going to do is step one is we will find X using specific volume, VF and VG, and then find U2 using X, UF, and UG. Okay. I'll show you both. We have time. I'll interpolate also, and you'll see it's the exact same thing. Okay. So for step one, let's find X. So our equation is that V2 is equal to 1 minus X VF plus X times VG. So I have VF from the table right there. And then I also have VG from the table right there. And then V2 is also given to us because it stays the same as V1, right? So we want to just solve for X. So we have that X is equal to V2 minus VF divided by VG minus VF. So we have 0.005 minus 0.0001252 divided by 0.050085 minus 0.0001252. Okay, and we get a quality of 0.0976. All right, so now we have X. So now we're going to use the equation that U2 is equal to 1 minus X UF plus X times UG. Okay. Okay. So I have everything on the right-hand side of this equation already. So I have 1 minus X, which we just found is 0.0976 times UF is in the table. It's 1080.7. Plus our quality again is 0.0976. And then UG is in the table right here. It's 2601.8. All right, and this gives us 1229.2 kilojoules per kilogram. Okay. Okay, so we have our pressure and we have our internal energy. Do you guys want to see the interpolation version of finding this? Yeah, okay. Okay, so alternatively, oops, that's a highlighter. We can find U2 by interpolating. So how we're gonna do this is we're gonna make our table and we have V and we have U. All right, so what we're gonna do is we're gonna have VF, V, and VG. And then we're gonna have UF. This is for two, U2 and UG. All right, so VF is 0.001252. V2 is 0.005 and VG is 0.050085. All right, U2 we want to find. UF we have is oh, right here. 1080.7 and then VG or UG is 2601.8. Right? So then we interpolate. So I have U2 minus 1080.7 divided by 0.005 minus 0.001252 is equal to 2601.8 minus 1080.7 divided by 0.00050085 minus 0.001252. All right, and we solve this for U2 and we will get the exact same value. Okay. If you're not specifically asked to find the quality, interpolation is a little quicker. If you're asked to find the quality, then you might as well do it that way. It's the exact same thing, right? Any questions on either of those ways? I don't expect you to do both on the exam. Like you can choose whichever one. Yeah,
Have a quality line is a mixture, right?
correct. So unless you're in the vapor dome, whether on the line or inside of the lines, that's the only time you have a quality. Outside of that, it does not exist. Okay? Other questions so far? No? Okay, cool. All right, so I'm gonna fill this into our table. So we found that our pressure is our saturation pressure, which is 3.976 MPa. Our internal energy is 1229.2. And then this is a saturated liquid vapor mixture. Right? Okay. Last state. Oop. So state 3. All right, so we have that the piston cylinder achieves a pressure of 4 MPa. So I've written 4,000 kPa in that table through an isothermal process. So this is a constant temperature process. So our temperature stays 250. And so what we want to do is we want to first figure out the state. So we have a pressure and we have a temperature. So what we should do is figure out what the saturation pressure is at 250 C or vice versa, figure out what the saturation temperature is at 4 MPa. Okay, you can do either way. Okay, so let's do that. Oh, we do. That's right. Thank you. What happened? Did I add a page like somewhere else? I thought I added a page. Okay, maybe we don't need a page. Did I delete something? What? That's what I deleted? Oh, no. Okay. Phew. That was a close call. Okay. Okay, so for state 3, so to find the state, use either PSAT at T3 or TSAT at P3. So you can do either one of these, doesn't matter. We already have PSAT, so let's write that down then. So we have 3976.42 kPa, right? And since PSAT at T3 is less than P3, that means that this is a compressed liquid. Okay. Okay, so I'm gonna write compressed liquid in the chart. And now I can use the compressed liquid chart to find, we wanna find V3 and we wanna find U3. So we go to the compressed liquid chart. Okay, so let's do that. Oh. Okay, we got compressed liquid. So this is arranged in the same way as the superheated vapors. We've got pressure cells for this one as well. So we want to go to 4 MPa. But we don't have it. Oh no, what should we do? Do you remember? There's an approximation we can make. So we're gonna approximate. So we do that V3 is approximately equal to VF at T3. Right? So always look up the saturation values for based on temperature, not pressure, right? Okay. This would be a handy little thing to put on your cheat sheet as just a suggestion. Okay, so VF at 250 is already up here. So we have this guy, right? And then we're also going to do the same thing for our U value. All right, so we're going to grab those two values. So we have that V3 is 0.001252, and this is meters cubed per kilogram. And then U3 is also UF at T3. So that is, 1080.7 kilojoules per kilogram. Okay. So I'm going to fill this back in the chart. So I have 0.001252 and then 1080.7. Okay. The hard part is done. So now we have all of our information that we need in terms of states. We did a little bit of practice with interpolation. We figured out what to do when we just had temperature and pressure. We did an approximation when we had a pressure that wasn't in the compressed liquid chart. So we kind of saw all of the things that we've seen in terms of complications, right? Okay, so the next thing that we want to do is we want to draw this on a TS or TV and a PV diagram. And now that we have all of the coordinates that go on here, as well as what state they are, we can put them in relation to the vapor dome, right? So let's do that. So I'm going to draw my vapor dome first on here. And then I'm going to also mark that we have a specific volume for 1 and 2 that's the same. I'm drawing it over to the right-hand side because for states 1 and 2, we're at superheated vapor and then also the mixture, so we can keep it over here. So for temperature, our temperature at state 1 was 500 degrees C. And then our temperature at 2 and 3 was 250, right? So my state 1 is here. So here's state 1. And then here's state 2. And this is 2. And then I connect them with a straight line. So on this chart, you don't need to draw it like perfectly to scale relative to the vapor dome, but I want to see that, you know, they have the same specific volume from 1 to 2. So it's just a straight vertical line. I've marked V1 and V2 and then the 2 temperatures on the axes. And I have that state 1 is in the superheated vapor region, state 2 is in the mixture region. Okay, so these are the sorts of things that I'll be looking for when I'm grading. And then for state 3, if you remember, it's an isothermal process. So we're staying along that 250 line and we're getting over to compressed liquid. So this is 3 and it looks like that. Any questions so far? No? Okay. Similar story for pressure. So I'm going to mark up, we have a starting pressure of 43 MPa. And then our ending pressure is, well, we have 2 pressures. So we have a like 3.9 MPa and then we have a 4 MPa. They're very close to each other. We have the exact same thing for the specific volume for pressure. So I want to see a vertical line because the specific volume stays the same. So we have our starting pressure is up here. And then our ending pressure for state 2 is down here. So we have this vertical line like so. All right. And then to get from 2 to 3, we have a constant temperature process, right? So our saturation pressure is going to stay the same inside of the vapor dome. So when you're moving through the vapor dome, it's always going to be on a flat line. Oh no. So we're always going to have a flat line through the vapor dome. And then we'll follow, this is an isotherm. All right, so this is our line of a constant temperature process. So we're always going to have a flat thing happening inside the vapor dome. So our process from 2 to 3 is going to look something like this. So flat through here and then it picks up just a little bit to get to 3. Okay. Oh, and I should have put V1 here. Sorry. So this is V1. Geez, 3. Thank you. Yes. Sorry. Any questions on drawing the process on the graphs? Does it feel okay once you have the whole table completed? Yeah.
For the line that you just drew, it's like going up as it's moving.
So these lines that I've drawn in orange, these are process lines for constant temperature. So if you have a constant temperature moving through specific volume and pressure, it looks like this. So these are all constant temperature. And then it does kind of a mirror image for the TV diagram. So this is what the constant pressure line would look like. So if you have a constant pressure, you're going to always have a flat temperature inside of the vapor dome. And then if you have a constant temperature, it'll be a flat line inside of the vapor dome on the pressure.
And so if we
Plot.
had, because if we have this problem, but it was a constant pressure instead of a constant temperature, we would draw those lines on the pressure graph, not the temperature.
So you don't have to draw me the isotherms or the constant pressure curves if you don't want to. I do it just because it helps me. So like for the pressure one, like to go from 2 to 3, since our pressure at 3 went up a little bit, the reason for that is because we went outside of the vapor dome just a little bit. So like inside the vapor dome, the line is flat. That's why I drew it. It's a good question. Yeah.
I knew where to put, you want to be on the x-axis.
So I just put it in a place that I knew if I went down from superheated vapor, I would end up inside the vapor dome.
Okay.
Technically, we know the quality is like 10%, so it should probably be over here. Like more to the left, but as long as you're in the vapor dome, I'm okay with it.
We don't have to label the x-axis of like the actual numerical values.
So if you label it this way and you've already populated them in the table, that's okay. The specific volumes are really long, like decimal place numbers, so it gets a little crowded. I'm okay with this. If you want to write them out, by all means.
What for the y-axis labels us? Or could you do P1?
You could do P's 1, 2, 3. Yeah, as long as they're like in the right order, you know, in terms of increasing and decreasing, that's fine. These ones were just a little more manageable to write, so I put them. Other questions? Okay. The last part of this is about work. Or I'm sorry, heat transfer and kind of work. So if there's no external work, so we don't have electrical work or shaft work done on the system, we want to find the heat transfer that happens from states 1 to 3, so Q13. So seeing this hopefully rings alarm bells in your mind that you want to use conservation of energy, because that's where Q shows up. So we will use conservation of energy, which is that E3 minus E1 is equal to Q minus W. And this is Q13, W13. Okay, so that's the same equation that's on the equation sheet, right? And we're gonna neglect kinetic energy and potential energy, right? So this means that we can rewrite our total energy as just mass times the specific internal energy. So we have mass of U3 minus U1 is equal to Q13 minus, and now I'm going to write out the work for 13. So we have 3 different types. It could be boundary work, electrical work, or shaft work, right? But we were told that we don't have these. Right, from that statement. Okay, so I have that MU3 minus U1 is equal to Q13 minus boundary work. We already know mass, and from part A, we figured out U3 and U1, right? So all that's really left is we need to do something about WB. Okay? So I am going to put in our definition for boundary work, which is that boundary work is the integral from some starting volume to some final volume. So I'll go from 1 to 3, P dV. Okay. And then I can also rewrite this as a 2-step process. So I have work going from 1 to 2 and work going from 2 to 3. Oop. So I have work from V1 to V2, PdV, plus work from V2 to V3, PdV. Is there anything convenient that happens for one of these processes? Yeah, so from V1 to V2, the volume stays the same, so there's no boundary work, right? Excellent. Oh, okay. And then we do have a change in volume from 2 to 3. And so I would have put this statement in the exam if this was your actual question. So we can assume that P is equal to P2, since P2 and P3 are pretty close, right? So if you remember, we had 3.9 something MPa and then 4 MPa, so that's close enough. We're gonna just assume that pressure's constant, okay? Okay, so we have then that mass times U3 minus U1 is equal to Q13 minus, oh, and one more thing, sorry. So if you remember, specific volume is volume over mass. So I can write dV as m times the differential of specific volume, okay? Because we have specific volumes, not total volumes. So I'm going to write it this way. So I have mass times P2 V3 minus V2. All right, and now we have all of the things that we need. So we have mass U1, U3, mass P2, V3, V2. We have everything, okay? So I have that Q13 is equal to minus 10 kilograms times 1080.7 minus 26.4 kilojoules per kilogram minus 10 kilograms times 3976.2 kPa. 0.001252 minus 0.005 meters cubed per kilogram, which gives us minus 1.56 times 10 to the 4th kilojoules, which is less than 0. So this means that heat is lost. Which hopefully makes some sense because we started with a super hot thing and then compressed it into a liquid. Yeah.
Mass is negative.
Oh, I'm sorry. So I took this minus sign showed up because I took this term. Oh, wait. Thank you. You're right. It should be positive. Thank you. Sorry about that. So the minus sign is because 2,626 is less or is greater than 1080.7. And then this number is greater than this one over here. Thank you for pointing that out. Any other questions? Yeah.
You have to get the integral in terms of specific volume.
No, if you want to take your specific volumes and multiply by mass to get volume, that's fine. Either way. Yeah.
Show the like number crunching on the exam, or can we just, even if all the units balance, we can just do a thing, or you want like the final answer?
Do you mean like this line? Oh, yeah, that's fine. If you don't, yeah, that's fine. Yeah.
So what you going to use like
So, I would have clarified if this was the actual exam, I would have said, use one or the other, or, I would have said something to that effect, or that would be a completely fair question to ask me. Which I would also write on the board, tell everybody what to do. Other questions? So this is the end of the exam. I know the third one was the most work, but did it feel okay? Not unexpected. Okay. I'm happy to answer more questions if you guys want, but this was all I planned for today. So expect the exam to look very similar to this. And yeah, just if you have oh yeah, go ahead. Sorry, which part? Yes.
If we have pressure, I mean, there's a past job, we want to be, we still have to put out there, he wants to make everything feel like that.
It either, way, as long as you put the unit and it's clear, either way is fine. But if you just write like 4, and I'm like, okay, what do you mean? Do you have a question? It is on Moodle, and I'm gonna print, I will print them for you guys.
Like,
Oh, for yourself, yeah, that's a good idea.
I did it in last semester, it was like 50 pages.
Oh, these ones I don't,
Nice to have.
yeah, just have them, yeah,
Thank you.
yep.
Can you explain why for state 3 it's compressed liquid? Because they
Oh, sure. So if, let me remind myself. So we have 250 and 4 MPa, right?
yeah.
So if we look at this table. So we have that at 250, so if this is P and V, so at our V3, we know that this line is 3.976 MPa, right? So we're right here. And then if we have our actual pressure is 4 MPa, right? So that means we're going up right here. So that means we're in the compressed liquid.
Oh,
We're on this side. Does that make sense?
yeah. Thank you.
Yeah, sure.